Yes, class. Am I audible to all of you?
Yes, ma'am.
Abhira, Anna, Iram, Marita, Sania. All right. So today let us start with magnetics. So see, we'll take 3 classes of magnetics. In the first class, let us complete Biot-Savart's law and Ampere-Circuit law. Because from Biot-Savart's law also you have plenty of questions. So we'll have Biot-Savart's law and Ampere-Circuit law. We'll try to cover it in today's class. Then you must have studied magnetic force on charged particle, Lorentz force, magnetic Lorentz force is there. Those portion we'll complete in the next class. And the last portion, that is conversion of ammeter, galvanometer into ammeter and voltmeter, those part and all, that we'll try to complete in the last class. So first let us revise the theory part of it, and all of you note it down also. I'll give you time. When I'm saying then do not write it, but when I'll give you sufficient time to note it down. Now see, in Biot-Savart's law, basically Biot-Savart's law says that if a wire is there that is carrying current within it, and if you mark a point, now you want to calculate the magnetic field on that particular point. So current will be, the magnetic field that is produced will be proportional to certain things. Now the first quantity that it is proportional to is current. Whatever is the current that is flowing within the conductor, magnetic field is directly proportional to the current. Secondly, if you take a part of the current of the wire, what will be having? The direction of current will be somewhere what was exactly the direction of original current that was flowing. So we call the segment of the wire as current element. So direction of current element is exactly same as that of current of the wire. So magnetic field is firstly proportional to the current that is flowing within this. Then secondly, it is directly proportional to the current that is flowing through it. Secondly, it is proportional to the current element. Then you have, if we drop a point, let's say this is the point where I want to calculate the magnetic field. And if I take the separation of this current element from this point P, so it must be having a certain separation. Let's say this entire separation is R. This is known as the position vector. So what was current element? Current element was the current that was flowing within the wire, a segment of it whose direction is exactly same as that of the original current. And position vector, this is R. So separation from point P to the current element is position vector R. And now this position vector R would be making some angle theta with the current element. Here you can see. So what Biot-Savart's law says that, this says that magnetic field is directly proportional to this current that is flowing within the wire. It is directly proportional to this current element, that is dl, directly proportional to this sine theta, and inversely proportional to the position vector square. So this will also follow square rule. Now, if you combine all of these, what will we get? dB is directly proportional to IDL sine theta divided by R square. And wherever we use this constant of proportionality, here also a constant of proportionality will come. Here I have written it K, but the value of K is mu naught by 4 pi. So mu naught by 4 pi is written as 10 to the power minus 7. This is similar to 1 over 4 pi epsilon naught. In electrostatics, we write 1 over 4 pi epsilon naught. In magnetic field, we'll write it as, magnetostatics, we write it as mu naught by 4 pi. So mu naught by 4 pi, value of mu naught by 4 pi is what? Value of mu naught by 4 pi, this is 10 to the power minus 7. So whenever you have to write mu naught, write it as 4 pi into 10 to the power minus 7 like this. So this is what is Biot-Savart's law. And yes, see, the SI unit of magnetic field is Tesla. But you might be needing this conversion to convert the SI unit into the CGS unit, that is Gauss. So remember this conversion, 1 Tesla is equal to 10 to the power 4 Gauss. This is the conversion which you have to remember. So this is... Okay, before we do that, firstly note down this part. All right. Next thing is regarding permeability. This is very similar to permittivity, which we study in electrostatics. Now, permittivity and permeability. Permeability is related to magnetostatics and permittivity is related to your electrostatics. Now, in permeability, this mu naught by 4 pi, no, just now which we have discussed, this is exactly what it is. So, mu is permeability in any medium, But if we specify that medium as air or free space, then that we write it, we put a naught in it. In the subscript, we put a 0. So mu naught, that is permeability of free space. Mu is permeability of any medium. So if you take the ratio of mu and mu naught, that is permeability in any medium divided by permeability in air. This is in any medium, this is in air. The quantity which we get is known as relative permeability. So you just have to remember these basic forms of permeability. That is, for ferromagnetic substances, relative permeability is greater than 1. For iron, this is exactly equal to 1000. For diamagnetic substances, this is less than 1. All right. So what do we do if you have another medium? See, what will be magnetic field then? Mu, it won't be mu naught because you have some other magnetic field, you have some other media. So mu naught I dl sine theta divided by 4 pi r square we'll have. But can we use mu? We do not know how to solve mu. We do not know the value of mu. So how to solve it? See, just now we have studied mu is equal to, from here, what can you say about mu? Mu is equal to mu naught into mu r. So if instead of this, I will put the value mu naught into mu r, I'll get this form. That is what is written over here. You will put mu as mu naught into mu r and you will get it for any of the media which you want. Direction, I'll tell you. First, note down this part. Do not write this example thing. Just write this relative permeability thing and this formula. That's it. Do not write this part. Now see, two directions we have, two rules we have for the direction of it. Now see, both the methods I'll tell you, but you have to practice this simultaneously. First method says that do one thing, that if let's say the wire is this is the wire, current is moving upwards. So take your right hand, we'll only use right hand thumb rule will be sufficient. So take your right hand, hold the wire in such a manner that the thumb points in the direction of current. Suppose we are taking this point. So if you place your thumb would be like this. upwards, pointing in the direction of current like this. So curvature of fingers will give the magnetic field's direction. See, at this particular point, if the thumb is pointing upwards and your fingers are curling outwards, there's like this way, no, fingers are curling outwards, right? So this is what is meant by this first method. Similarly, if you take this point, if I talk about, still I'll put my thumb in the right hand side. Now at this particular point, just check. See, at this particular point, if you see here, what will happen? Here you will notice fingers are going inwards like this. Fingers are moving inwards. So what will happen? At this particular point, the fingers are moving inwards. So this is known as first method, in which you are finding out using the pointing the thumb in the direction of current. All right, suppose if I give you a different point, let's say, take this point. Put your thumb in the direction of current and curl your fingers towards a point. Curl your fingers at a point. See whether the fingers are pointing towards you or they are moving to the screen. All of you reply me in the chat box quickly. If I give you this line and the current is moving towards the left, so keep your thumb towards the left. At this particular A point, see, are the fingers coming out of the page or are they moving? Are they moving inside? So only Marita got. Some are getting in, some are getting out. C class, you have to place your thumb in a direction where the current is moving. So where is the current currently? Current is moving towards the left. Use your right hand only, class. Just to use your right hand. Wait, let me show you. Current in this case, this is moving towards the left. So I'll take my right hand. I'll also place the thumb in such a direction that this is pointing towards the left. See the screen and see the video. Both are parallel, both are aligned with each other. My thumb and the direction of wire, both are aligned towards each other like this. Now, where is point A? If this is the current, point A, is it located here or is it located here? It's located below. So my point is here currently. This is the point A. So at particular point A, I have to check, right? So I have kept my thumb like this in front of it. All of you do it simultaneously, then only you will be able to understand. Keep your thumb like this. Now at particular A point, if I place my hand in the screen, fingers are, where is the direction of fingers? Like this, you have to check. If this is the point, keep your fingers on the point. Put the thumb direction and at that particular point, check. Your fingers, see, the fingers are pointing towards me. If I show you like this, the fingers are pointing towards me, right? So this is outside the page, not inside. One more method, let me tell you. I think this will become confusing. This is much better to study. Instead of keeping the thumb in the direction of electric current, keep your fingers in the direction of electric current. In such a manner, where the current is pointing, your nails part should point there, right? So suppose in this part, in this question, let's take this example, red question, this red one, A. Fingers are pointing towards the left side. A current is going towards the left side, so I've kept my finger towards the left side. Now I have to curl my fingers towards a point. Now when I say keep your hand in such a manner, right hand in such a manner that the direction is towards the current's direction. See, I could have kept it like this. I could have kept like this, palm facing towards me. I could have kept it like this also, palm facing upwards, right? I could have kept it like this also, facing towards you. So firstly, I cannot put it like this because this is not the direction of current. I have to keep it anyways in this manner, either this, or this, right? So how should I decide? I could keep it like this also and get my answer. No, I have to choose such a direction when so that I'm able to curl the fingers towards point. See, point A is located downwards. If I'll curl it this way, this is getting curled in front of me. Point A is downwards. So obviously this is not the correct position. If I keep it pointing towards you people, right? Point A is here. If I'm curling my fingers, is the curling occurring towards A point? No, this is somewhere here. If I keep my palm like this, now if I curl it, can you see? Now this is getting curled towards A point, which is downwards. Where is the thumb pointing? Thumb is pointing towards me. That is out of the screen. So outwards, like this also. All of you tell me for this particular pointing. Use any of the methods. Both the methods I've told you. I'm repeating, just quickly listen for both the methods. First method says that place your thumb in the direction of current. Suppose if you put thumb in the direction of current, at the particular point, just check, are the fingers coming out of the page or the fingers going into the page? If this is the case, fingers will be going out. If this is the case, fingers will be coming, right? So outside, inside regarding this. Second method says that, which also I also prefer the same method. Put your hand in the direction of the current in such a manner that you are curling it towards the point and the thumb is giving you direction. Now, all of you tell me for this particular A point using any of the methods in the chat column quickly. So only Marita and Heather have answered. Samira, Anna, Heather, Marita. Yes, correct. See, if we keep the right hand, see, consider just use your right hand only. If we keep our right hand along the direction of current, so where is the current pointing? Current is pointing upwards. So I'll also take my hand. This will be pointing. This is the right hand. This is pointing upwards. So whether I should keep it like this, I should keep it like this, I should keep it like this is determined by the point where I have to find out the magnetic field. Point is located here, right? This is exactly what you are looking at the screen. So point is located exactly to the left of the current element, wire. So if I keep my hand like this, if I'm curling it, is the curling occurring towards the point? No. So if I shift it like this, now if I curl it, so point A is located here towards the left side, and the curling of fingers is also occurring towards the left side. So both the things have been satisfied. Now where is the thumb pointing? Thumb is pointing towards me. That is out of the page. So it is outwards only. All right. Tell me, all of you now, all of you should answer this, not only these 2-3 students. For this B point. This is the wire, this is B point. Heather, Marita, Anna, Sumaira. Yes, Arpit, Sania. What are your answers? Abhinav. See, Sania, look here. Now the current element is pointing downwards, right? The direction of current is downwards. So how will you keep your hand? In which direction the fingers should point right now? Yes, Sania? See, we keep the hand in the direction of current. So right now I'll take my right hand. This is pointing downwards. Yes, down, right? So I have to curl my fingers towards the right, because B point is located towards the right of the current wire. So if I curl it towards the right, again the thumb is pointing outwards, right? This is pointing towards me. So this is how you determine whether the direction of magnetic field, whether it's outwards, outwards or inwards into the page or out of the page. Fine. So these are the two rules which you have to remember. Just write down the methods. Just quickly write down the methods.
Done, ma'am.
All right. Now see under Biot-Savart law, under the applications of Biot-Savart law, few formulas you should remember. So quickly we'll discuss the formula only because derivation is of no use right now. So magnetic field due to straight wire we'll see. So three cases are there: finite, infinite, and semi-infinite. And circular wire we'll see. So under circular wire also you have circle, semicircle, and arc. Arc which is subtending a random angle. All right. So magnetic field due to infinitely long wire. If the magnetic field is due to infinitely long wire, so when we say infinitely long wire, it means both the ends are extending from plus infinity to minus infinity. Now at this particular point, you have to find out the magnetic field. So mu naught I by 2r. So if this is semi-infinite, so for semi-infinite, just half it. If this is mu naught I by 2r, this is going to be mu naught I by 4 pi r. Now, what is meant by semi-infinite wire? Semi-infinite wire means when one end is only extending towards infinity and other end is fixed, other end is finite, one end is only towards infinity. But the point of calculation that we are taking is located towards the finite point. So this is it. So just make the headings: magnetic field due to infinitely long wire, just write it. Then make the heading for semi-infinite and just write the formulas. This one is for semi-infinite. And yes, one more thing, you have finite wire as well. So see, magnetic field when we have to find it for finite wire. Now in case of finite wire, both the ends are fixed. Now we are taking a particular point, let's say P point we are taking. So what we have to do, we'll just take the angles that have been subtended by the edges of the wires. Let's say this is some angle, this is also some angle, theta 1, theta 2. This is the separation A which we refer. This is the finite wire, the length of the wire is fixed. So what will be the formula of magnetic field? If you remember the formula of finite wire, you will be able to derive the formula of infinite and semi-infinite as well using the angles. So this is mu naught I, current I is flowing across the wire, mu naught I divided by 4 pi A. A is the separation, which is the position vector we choose in Biot-Savart's law. Sine theta 1, this is the angle subtended by the first edge, plus sine theta 2. So this is for finite wire. Now see, if this is infinite, for infinite, what happened? This keeps on extending. So the angle that gets subtended at the point of calculation, that becomes 90 degree. So your theta, this becomes 90 degree. If it is in completely long wire, which is extending to infinity, infinite wire, so this angle will also be 90 degree, this angle will also be 90 degree. If it is semi-infinite, so in semi-infinite, what will happen? Only this angle that will be subtended here at this point, this will be 90 degree. Whereas the second angle, theta 2, which was to be subtended from the other edge, now since the point is lying towards the end only, this angle becomes 0 degree. So theta 1 will be 90 degree for semi-infinite and theta 2 will become 0 degree. All right, so just write down the formulas for it. This I think you have written, no, semi-infinite. This is just for finite. Then we'll move on to circular arc form. All right, now regarding the circular wire. So you have a circle, you have a semicircle, and then a random arc, which is subtending certain angle at the center. So if we are talking about a circle, at the center of the circle, which is having radius r, current I is flowing across the circle, magnetic field is given by the formula mu naught I divided by 2r. And as soon as this becomes a semicircle with radius r, with current I flowing towards it, this becomes mu naught I by 4r. So mu naught I by 2r is for a circle, and magnetic field at the center of a semicircle, this is mu naught I by 4r. But if it's an arc which is subtending an angle, suppose this is an arc, this is subtending certain angle towards the center. This angle is, let's say this angle is alpha. So magnetic field, let's say the current moving is I, radius is r, the radius across this is r. So the magnetic field now, because of this segment, this is going to be mu naught I alpha divided by 4 pi r. So whatever angle is being subtended, just put in the values of alpha and you'll be getting different values of magnetic field across it. So if it is at a certain angle, use this formula. Circle and semicircle are fixed. That also you can get it using putting the values of it. And now see direction for circular wires. Finite wires we have seen, for long wires. Now in case of circular wires, see, we have to curl our fingers. Again, we'll be using the right hand only. We have to curl our fingers along the sense of current. For example, look in the second figure that is given. So I'll curl the fingers along the sense of current. In which direction is the current moving? Current is moving anti-clockwise in this. So I'll also curl my fingers anti-clockwise only. All right. Now, where is the thumb pointing? Thumb is pointing outwards. It means at the center of this particular circle, the magnetic field's direction is outwards. So if I curl the fingers, you have to curl the fingers along the sense of current. Here in the first figure, if we look in the first figure, all of you look here. Try this along with me only. The current's direction is clockwise. So if I curl it like this is going to be anti-clockwise. So I have to choose the direction as clockwise, like this. This is clockwise, thumb is pointing towards the screen, that is inwards. So this is how we choose the direction for circular wire. All right, now we'll be practicing questions. In questions, we will not be having just one simple figures, we'll be having combination of all the formulas which we have studied. But just before that, just note down the formula part of this circle. Yes, one more thing, class. See, this is all these formula just for a single turn. If a single turn is there for a circle, if a single turn is there for semicircle, but if n number of turns are there, right? N number of loops are made. So whatever is the number of turns, just multiply it here. N mu naught I by 2r. If it's a single turn, then n is going to be 1. So that is going to be mu naught I by 2r. If n is 2, so 2 mu naught I by 2r, like this. Similarly, this is case for semicircle and similar is the case for angle, that is arc. This is the formula for arc only, where n is the number of turns. Note it down, note the direction, then we'll practice some questions. Written class.
Yes, ma'am.
All right, let us practice some questions now. So this question, this says that a long solenoid of 50 centimeter length is having 100 turns, carries a current of 2.5 amperes, magnetic field at the center of solenoid. Solenoid we haven't discussed right now. Ampere circuit law we haven't discussed. Let's discuss Ampere circuit law as well. See, Ampere circuit law says what? Ampere circuit, under Ampere circuit law, we have the line integration. I'll show you the law. See, suppose this is the line integral of magnetic field. Line integral of magnetic field, we write it as B dot dl, integration of B dot dl, a closed loop. This we write it as, this is the line integral of magnetic field. So this is equal to mainly mu naught times permeability we have just discussed, permeability of free space, permeability in any medium, relative permeability, permeability, all these things we have discussed. So this is exactly mu naught times the current that is enclosed. So this is similar to Gauss law. Under Gauss law, when we were discussing, we had studied all the charges that are getting enclosed within the Gaussian surface will only be included. So under Ampere circuit law also, we'll choose an Amperian loop. Under the Amperian loop, whatever charges will be getting enclosed within it, plus I1, plus I2, minus I1, we'll include these only, whereas the charges I3, I4, which are lying outside the Amperian loop, closed Amperian loop, that we'll not consider. So B dot dl is equal to mu naught I enclosed. This is the law, Ampere circuit law. So according to Ampere circuit law, line integral of magnetic field along a closed loop, this is mu naught times the total current enclosed by the loop. So just write down Ampere circuit law. Do not write this law, just write down this formula for Ampere circuit law. See, under the applications of Ampere circuit law, we have two devices. One is solenoid, other is toroid. Now, what is a solenoid? Solenoid is basically windings of wire, right? Now, if we just turn the solenoid into the form of a circle, in circular form, that is known as toroid. So formula for both of them is same only. B is equal to mu naught Ni. This is the formula for it. B is equal to mu naught Ni. Now, see, difference lies in, let's say L is the length of the solenoid having n number of turns. So n is the number of turns, L is the length of the solenoid. Now the definition of n in the small n in this formula for solenoid is number of turns per unit length. That is capital N divided by L. N is equal to capital N divided by L. That is the number of turns per unit length. But when we are talking about toroid, under toroid, this is suppose radius will also be there because it's in the circular form. So now the value of n, the definition of n, this is number of turns per unit length. But what is the length of a circle? Circumference of a circle, 2 pi r. So this is number of turns. N is capital N is number of turns. And this is the circumference of the circle, 2 pi r, where r is the radius of the toroid. So this formula only you have to use. B is equal to mu naught Ni. Mu naught's value also we have discussed. This is 4 pi into 10 to the power minus 7 we'll use. I is the current in this formula, and N is number of turns per unit length. This is not just the number of turns. Capital N I am referring to as the number of turns. All right, just quickly note down this page as well.
Then
Others have also written. Just text me done in the chat column if all of you have completed this. Now I think we'll be able to solve the questions of solenoid and toroid as well. So this says that a long solenoid of 50 centimeter length having 100 turns carries a current of 2.5 amperes. Magnetic field at the center of solenoid we have to find out. See, length of solenoid, this is given as 50 centimeters. Number of turns, these are provided as 100 turns. Current is 2.5 amperes. Mu naught's value is also given. Magnetic field at the center of solenoid. So B is equal to mu naught Ni. This is what we have discussed. Yes, what is the value of N that I should take? See, mu naught is very clear. Mu naught is given here 4 pi into 10 to the power minus 7. Current is also given 2.5.
100 by 50.
100 by 50, right? Number of turns per unit length we have to write. This is number of turns per unit length. So number of turns is 100, per unit length is 50. Yes, Marita, right answer. Correct. Option D. So number of turns per unit length. Now magnetic field mu naught will be 4 pi into 10 to the power minus 7. Number of turns, these are 100. 50, this is 50 centimeters. So it's better if we write this as 0.5 meter. So 0.5 and current is 2.5. When you solve this, you should get here the answer as 6.28 into 10 to the power minus 4 Tesla, which is option D. Quickly write it down. Some other questions we'll see then. So this question says that two toroids, 1 and 2, have total number of turns 200 and 100 respectively, with average radii. One is 40 centimeters, other is 20 centimeters respectively. So two toroids are given and they are having the same current. So current is same, number of turns are different, radii are different. You have to find out the magnetic fields across the two loops. So which is the formula that we should use for toroid?
You're not like
Mu naught.
NI
What is the value of n that we should put?
N by L 200 by 14 to
N by 2 pi r. N
yes,
by
N
2
by
pi,
2.
right? So mu naught, this is small n, we write, so either is right, we write it as mu naught ni, but the value of n that we'll put will be n by 2 pi r that we'll put. So this is going to be mu naught ni. This is 2 pi r. This is the general formula. So you have all the details about it. You have the number of turns for the wires as well. You have the radius as well. You have the currents as well. So for the first one, this is going to be mu naught. Let me write it as n1. I is same. 2 pi. Radii are also different. So r1 and b2. This is going to be 2 pi r2 by mu naught n2 I. So mu naught I gets cancelled. From here 2 pi also gets cancelled. So what we'll write for b1 by b2, we just have to substitute the values n1 by n2. N1 by n2 and this is r2 by r1. So N1, this is 200, this is given as 100, and this is 40 and 20. So R2 will be 20, this will be 40. So this is going to be 2, here also we'll have 20. So 20 by 20, that is 1 by 1. So ratio will be 1:1. So option A. Correct answer is option. So this is, yes, Heather, yeah, Heather has already answered. Yes, noted down. And please note down the question number as well. This is from your previous year, so you already have this material. So just note down the question number as well, because if when you'll refer to the questions back without the numbers, you'll face difficulty. So this is just question 2, which we did, and this is question 3. So just put the question number and then note down the solution. See, for this particular question, no, yes, Marita, your answer is correct. You just have to remember two formulas, and then whether it's outside or inside, depending upon that, you can get your graph as well. Heather is also correct. See, question says that a thick current outside, a thick current carrying cable of radius r carries current I uniformly distributed across its cross section. So variation of magnetic field B due to the cable with a distance r from the axis of the cable, that we have to write down. See, magnetic field inside a conducting cable. We write magnetic field inside a conducting cable or a cylindrical wire if you choose, concentric cylindrical wire if you choose. So this is mu naught I divided by 4 pi r square multiplied by this r. This r is Amperian loop's radius. This is Amperian loop's radius, and capital R, this is the radius of the cylinder which is given, a radius of the cable. So if suppose like this is the wire, this is the cable wire, some radius must be there of this wire, that radius is capital R. If we are choosing a point inside of it, so radius of this Amperian loop that we are choosing, this part, this is small r. So just remember the formula. The formula for this is mu naught I r by 2 pi r. But if we write the formula for outside, formula outside is mu naught I by 2 pi r. That's it. So see, can you see the variation with r? Here magnetic field, this is directly proportional to r. See, this is directly proportional to this r. And here what is happening? R is the distance from the axis of the cylinder. Now see, here in this second case, if you look in this formula, be outside. So point outside the cylinder, here magnetic field, this is inversely proportional to R. Now, when the radius, in this case, this means if this is the wire, the radius of the wire is R, we are choosing a point that is located outside. So this will be the Amperian loop. So radius of this Amperian loop will be this smaller. It will be enclosing all the current. So derivation is there, but we do not need a derivation right now. So formula will be this. So initially look, C point is the correct answer here. This is directly proportional, you can see. B is directly proportional to R, and this is getting inversely hyperbola you are getting because this is inversely proportional. So variation is due to with R is from the axis is like this. So correct option is C. Yes, class. Try this question first. Let me know your answers. I'll discuss it then. So only Marita could try. No, Marita, that is the wrong answer. Anyone else? See, what is the angle that is subtended here? This is 90 degrees. What is the angle that is subtended? No, Abhinav. This angle, how much is this angle? This is 270 degrees, right? This is 90 degree, this is 270 degree. I2 is flowing. Now, if we calculate magnetic field due to this larger segment, let's name this as something. Let's say this is point is A, this point is B. So magnetic field due to this larger segment, if we find out, I'll write it as larger only. This is, what is the formula that we discussed? Mu naught I into alpha divided by 2r, right? To a 4 pi r. So mu naught I1 is the current that is flowing here. Look, across here, this is current I1 that is flowing. So this is mu naught I1 divided by 4 pi r and alpha 270. We can write this as, this is 270 degree. So we should write it as 270 by 2 pi, right? This is how we write the formula. Mu naught I into this, or directly write it the angle. Directly you can write down the as 270 because 4 pi r we have it. Now similarly, magnetic field due to the smaller segment. This is mu naught I2 by 4 pi r. This is 90 degree, basically pi by 2. This is pi by 2 that we have to write, right? So net magnetic field, resultant magnetic field, this is mu naught I1 into 270 by 4 pi r plus mu naught I2 into 90 by 4 pi r. Right? This is how we write. But see, two arcs, you can also see this as parallel combination also. If the wire is here, it's like if this part you are connecting a resistor here, wires are there along with the battery, and this part is forming another resistor. Isn't it like this? Parallel combination. So if the wires are in parallel combination, that means potential across both is same. V1 is equal to V2. That is I1 R1 is equal to I2 R. So if the length of the wire is also uniform, right? The length of the wire is also uniform and resistance is also same. Resistance is there, resistance isn't same. Resistance you can take it as, see, R1 by R2, you can take it as L1 by L2. This is directly proportional to length. So length, you can write it as R into radius into length of arc. How do you write? Radius into the angle. If angle is subtended, this is the length, this is the radius. This is how we write the relationship between the radius. So this is going to be R into 90. So I1 by I2 from here. This is the same thing. No? I1 by I2 is R2 by R1. This is going to be 90 by 270. That is 1 by 3. So now you have the values of currents with you. I1 is equal, or you can say I2 is equal to 3 times I1. In the above equation, which we were not able to solve, this equation, this wasn't getting solved because of current only. No, current was hindering over here. So now you can just put in this value in the equation which we have just got. In this equation, you can put this value of I1 or I3. See, when you will put it, resultant magnetic field, this is mu naught by 4 pi r minus 270 I1 plus 90 I2 is there. This is what we have still here. And why am I writing minus 270? See the direction. This is clockwise here, right? So curling your fingers along the sense of current, this is going inwards, right? If you curl your fingers, this is going inwards. And whereas this is anti-clockwise, this is outwards. So inwards, this is inwards, and that is outwards. That's why this I have written it as minus. So B resultant, this will be mu naught by 4 pi r This will be minus 270 I1 plus 90 and I2. What can I write I2 as? 3 times I1. Now I have one single relationship with I1 only. So 3 times I1. What exactly is 3 times I1? Mu naught by 4 pi R minus 270 I1 plus 270 I1. See, they are getting cancelled. This is C. So resultant magnetic field is 0. So option, I think A, or which option? Yes, A option. This is the right answer. Note it down.
So, ma'am, if we consider I2 to be the larger current and take the magnetic field of that greater, and then find that it is outwards, doing that will be wrong, right?
No,
Because we
see,
don't know the exact magnitude.
see, even if you do that, the same thing exactly. We don't know the same know the exact magnitude, but since we are knowing that this area is larger, so a lot of current is flowing here. That's why we are taking this as B1 and B2. We are taking B1 is greater than B2. This is for sure. No, angle is more. We write the formula.
Yes, ma'am.
Magnetic field is directly proportional to angle alpha theta. Let me write it here. So here also, if you write this, B1 is obviously greater than B2 in this case also. Direction is mentioned, not mentioned exactly in the sense directly, but current direction is given. So using that, you know the direction of magnetic, and you know B1 is greater than B2. That's why we are substituting it like this. But even if we change it, no, we make this as plus, this as minus. So that time also we'll get it as plus 270 I1 minus 270 I1. That will also give you 0. But don't go by that, because in this case you'll get the answer. But if some other question is there, you'll get stuck. Right? So just go by the area, by the angle. If this is the greater angle, this will be more magnetic fields, magnitude will be there, and this will be this. Fine?
Yes, ma'am.
Please use the directions. Circular one, wires. No, Marita. Wrong answer. See, a wire carrying current I has the shape as shown in adjoining figure. Linear parts of the wire are very long and parallel to x-axis, while semicircular portion of radius r is lying in YZ plane. You have to find the magnetic field at point 2. See, let us divide it into 3 parts. No, Marita. This is the first part. This is the first part. This is the second part. And this is the third part. So if we write B1 magnetic field, this is the segment, is a finite wire. This is a semi-infinite wire. This is extending towards infinity. This is at the center. So we'll use the formula mu naught I by 4 pi r. Now use the rule which we have studied, right hand thumb rule. Your right hand will be pointing towards the current, right? Current, this will point towards the current which is moving. And then if you curl your fingers towards point O, this will be inside. So we'll write it as minus K cap, that is negative Z axis. Similarly, for the circular portion, this is mu naught by 4 pi You can write it as mu naught by 4 pi as well, because this is just a semicircle. So mu naught I by 4r also you can write it, because that is the formula for it, and is again same thing, minus k. And for the third thing is the same thing, mu naught I by 4 pi r, if you write it exactly. So see, B2 will be mu naught I by 4r. This will be current's direction. Current's direction, this is not clear here. Current's direction is actually this. This is the direction of current. So if you curl your finger, this will be pointing inwards. Inwards is this, you see this axis which is not mentioned. No, this axis is actually, this is x axis. This is not given. This is z axis. This is y axis. All right. Now see. So D3 will be, this is going to be minus I cap, because it's going inwards, negative x axis. See, this is positive x axis is given to you. Positive x axis is already given to you. So inwards will be the negative z axis, x axis. And this is similar, mu naught I by 4 pi r minus k cap. So when you summarize B net, this will be, see, mu naught I by 4 pi r we can take common. So what will be left from here? Minus k cap, that makes it minus 2k cap. Let's take minus also count, because minus is already there, no? This. So this is going to be 2k cap minus 4 pi we have taken common, no? So we'll just multiply pi over here and I cap will be left. So which option? First option, A option is correct. Note it down, class. Text me done once done. All right, those who have completed, you can leave. We'll continue the rest.